So today we're going to finish up with error handling, and then we'll focus on how error handling is handled in Java, since we haven't really covered that yet. It's through exceptions. But basically what we covered on Wednesday is that errors can be either completely unexpected or anticipated, but in any case it's not the normal control flow. Some errors are by nature fatal, right? The program should die if something happens. If there's no a wrong password or something like that, you could pre-prompt them, reprompt them. But if there's something that just cannot be recovered from, like no internet at all, or bad memory or something like that, you run out of memory, then some errors are going to be fatal, and you should quit out of the program. But some errors, and the ones that we're taking care of, are the ones that you can recover from. You can anticipate that somebody would enter the wrong password, and then you can handle that situation like by reprompting them or reporting the issue to security or something like that. Or you can look at like, I'm about to divide by 0, right? Some dangerous operation, and you see that you're about to do something, you don't do it. Otherwise, that would result in, bad behavior or undefined behavior. And all of this stuff collectively is known as error handling. Now, both languages, C and Java, approach error handling very, very differently. In C, what you have is defensive programming, right? In other words, the analogy I gave last time was looking before you leap, right? You write code to detect potentially dangerous or bad operations before they occur. Am I about to divide by 0? And if I am, instead of executing those operations, you stop and if in a function, return with an error code. Right? You do not exit nor print anything. Now why? If you exit, then you've taken away the decision-making ability from whoever is actually using your library, using your function. And maybe they didn't want to, exit, right? We're going to reprompt them for that password. You shouldn't reprompt them for that password. You should be giving that decision-making ability back to the calling function. So you do not exit, and you don't print anything, because there's not somebody sitting there watching the console 24/7, waiting to jump into action when something occurs. It is completely appropriate to log it to an error system using a proper logging system. You log it to system logs so that somebody can come back and say, all right, well, we had a problem at 3 a.m. last night. What happened? They start their analysis by looking at the system logs. Who was logged in at the time? What were they doing? Et cetera, et cetera. But you don't print anything to the standard output because nobody is sitting there staring at the console. By convention, 0 equals no error, right? It's false. Non-zero means some kind of error. There we go. Unhighlight that there. All right. And best practice dictates that you use human-readable messages, right? Human-readable terms, I should say. And this is either going to be using a define macro, right? Define, or an enum. Right? And we'll review that here in a second. Okay. Well, what about Java? Java takes a completely different route. Why? Because Java is a modern programming language. Java uses exceptions. It is okay to leap before you look, because if something bad happens, we will catch you and throw you back up, right? So this is why I use that look before you leap analogy. If you're about to walk off a cliff, right? In C, defensive programming means that you look ahead. Am I about to walk off a cliff? If so, stop. Don't take another step. Turn back around and go back where you came from. In Java, it's perfectly okay. Just keep walking, right? Because when you fall off that cliff, we will catch you, and note here that I've highlighted it as an actual keyword in the Java language. We will catch you and then throw you back up onto the cliff for you. And then you can decide what to do. Do you continue walking? Do you exit out of the program? Do you issue an error message, right? So that is a modern way of handling, of doing error handling in programming languages. C is rather old. It doesn't have explicit exceptions. It's got traps. You get caught in a trap so that we can, isolate this, but we won't go into that, right? So again, to review defensive programming in C, right? You design functions that such that the actual return value is communicated using pass by reference variables. That way, it frees up the return type to be an integer or an enumerated type, right? Once you've got that, then you've got an error code, right? The integer indicates the type of error encountered. Now, as you'll notice here, or as you'll note, the standard libraries don't take this approach, right? The standard libraries, right? Libraries use an error no .h library. Now, you're not going to be using that stuff, and you shouldn't be writing your own because it is part of the standard library. But at a much lower level, at a systems level, this is taken care of by the C standard library error no. This stands for, error no means error number, right? Don't ask me why. I think it's pretty British to call it NO instead of num, right? But whatever, that's what they did. Here is the documentation, right? It actually only defines 3 errors: EDOM, ERange, and illegal sequence. So DOM is short for domain. So if you remember a function, right, we're calling functions. So function is calling function. We're giving it input and it's receiving output. Well, EDOM is the set of the domain is the set of things that you map from. The range is the set of things that you map to. So if I were to say, you know, square root of 2, right? It's 2 is in the domain and it maps to 1.41 whatever it is, right? So that's in the domain, that's in the range. If there's an error in the domain, in other words, bad input, square root of -1, that's not defined, then an EDOM will be set. If there is an error in the range, in other words, an error in the result, then an ERange will be set, okay? And otherwise, an illegal byte sequence, that's, I cannot give you a demonstration on forcing something like this, but I can with the other two. Right? Let me go ahead and show you some code here. What was it called? Error demo. There we go. So I'm bringing in this error no library, right? Error number library, and then I've set up a couple of experiments. It is perfectly fine to take the square root of b when b is 2. Right? The result will be 1.41 whatever. And what we're going to do is we're going to print out the error number. Right? Now, what was the convention again? If there's no error, this should not result in an error. So error number, when I print it out as an integer, is going to be 0. Right? What happens when I try to call the square root of -1? Well, that's going to be an error in the domain. So we'll go ahead and print out the error number then. Right? Don't worry about the rest of this. Let's just go ahead and look at it as a demo. Right? We'll come back to that. Oops. What do I forget? -lm, great. A dot out. Now, ignore the rest of it. There is that good result. 1.41 and change, right? And what's the error? 0. But the result of square root of -1 is not a number. The error has been set, the error code has been set to 33. What was 33 again? Magic number, right? So, in the code, we actually use, in the code, we actually use the term EDOM, right? And you can check it. Is the error number been set to EDOM, or was it set to ERange, or was it set to the illegal byte sequence? And that's why you're getting this printout right here. It was an EDOM error. Let's take a look at another example here. By the way, you can also get human readable error messages out of this by calling string error. So you give it the error number and it'll give you an error message of some sort. It's not really helpful though, is it? Error message is numerical argument out of domain. Right? Well, yeah, all right, that's what an EDOM is. Right? So let's take a look at the second example here. If I take the log of C, where C was set to be 0, is that going to be defined? So think about the log function and how it's graphed. What is it at 0? Undefined. If I were to define it, we would have a name. What would it be? Negative infinity, right? So what happens? Well, that's out of our range of mapping values. So an ERange occurs, and this gets printed. And in fact, it does end up as -inf, right? Symbolically, and then 34. Again, 34 is a magic number, but if you use the ERange keyword, it's not a keyword, it's a preprocessor directive, then you get this, and here is the error message. Numerical result out of range. Now, unfortunately, the C standard library only defines these three at all. So everything falls under one of these three categories. Fortunately, there are extensions to this. Here's the full list of POSIX compliance error codes. EPERM, operation not permitted, right? EIO, there was an IO error, right? Input-output error. eChild, no child process. So a child process is when you have a program that launches another program that's a child to that parent, and then you can have orphan processes that need to be tracked down. Device, resource, or busy, right? The file exists, you can't create it, right? Various stuff. Now remember what those numbers were? EDOM, right? There it is, 33. eRange, there it is, 34. Right? Too many symbolic links encountered, a whole bunch of other stuff here. POSIX compliance codes, you have up to 131. I remembered it yesterday. Do I still remember it? That a seg fault is 139. So where is it here? I don't know. Seg, nope, it's not here. So it's probably not a POSIX compliant code. In other words, you've got a whole bunch of standards out there. You've got the C standard, you've got POSIX standards, you've got GNU extensions, right? And each one of these defines its own set of errors that you can use if you're using that library. POSIX stands for Portable Operating System Extension, I think, right? How do I get IX out of that? I don't know. But that every single operating system out there today is POSIX compliant except for one, and that is Windows. Yeah?
Would it kind of make sense to not have that one standardized because each device is going to deal with memory differently?
Yeah, but they're going to be the same general errors. And again, this is one standard. If you're writing your own code, like we were yesterday in mymath.h, I think, yep, then you would write your own, right? Yeah. Now, if you are doing systems level programming, then you would bring in that library and use that library all over the place. But this is user land errors. In other words, we're the users. We're not actually the users. Like consumers are users, but when we say users, we mean programmers. And so if I'm writing my own custom library, like my math library right here, then I define my own errors. Now the way that they did it over here is through preprocessor directives. Define EBADFD to be 77. The way that I showed you over here in my math was an enumerated type, right? And which one is better? There's not really a contest. It's whichever one you want to use. I slightly lean towards enumerated types because they survive the compilation process. So preprocessor directives, remember, it's just a cut and paste. So if you're debugging in a debugger, which we'll eventually get to, right, you will lose all of those symbols. If you just use define, no error, define, overflow, those get replaced with 0, 1, 2, and 3, and you're back at square one with magic numbers in your debugger. So I think that there's a slight argument in favor of using enumerated types. Right? So you can use those not just with errors, but in everything. Right? Many pieces of data have small or limited number of possible values. Days of the week, months, or error codes. When you have this situation, right, or levels of class, freshman, sophomore, junior, senior, right? When you have this list that it's only these possible values, right, and nothing else, and this list is not changing every day or something like that, then you can use an enumerated type, right, to give it a human readable name to them. And the example that we did yesterday was error codes, Wednesday, excuse me. Here's another example to remind us of how it works. So remember that we use the keyword type def. Go all the way down there. There we go. And what we are doing is we are defining a type. And what's the type that we're defining? An enum. There are other types. We will get to them. Structures. Right? And then we give it a name, but we want to give it a name at the end, day of week. And then followed by a semicolon because it is a declaration. I am declaring a type. And then you give it a list, Sunday. Right? We agreed that it begins on a Sunday, Monday, Tuesday. All right, as I'm writing these, do we know what these are named for? Sunday is, of course, the sun's day. Monday is the moon's day. What is Tuesday? Does anybody know that? Tyre's day? Right? Roman god, I think. I don't know. I'm not sure about Tyre, but a Wednesday. Now that's from Norse mythology. No? Whose day is that? Odin's day, right? So it's Wednesday, it's just another pronunciation of it. Thursday, that should be clear. Thursday and Thor's day. Friday is Freya's day, all from Norse mythology. Saturday is from Saturn, right? And then, of course, you have that coding Oxford comma at the end if you want to put it. Again, it is optional, right? But they're not adding any more days of the week, right? So you can use this. But be careful. In C, these are just integers and can be treated as such, but should not be. Right? What I mean by that is that you can do something like this. I can say day of week, today, is equal to Friday. Yay. Well, what if I did today plus plus? I can do that. What does it become now? It's Saturday. Right. What if I did it again? Today plus plus. Now it's, careful, 0, 1, 2, 3, 4, 5, 6. So it's now 7. It's day 7. Do you see a 7 up there? Nope. But it's an integer, and it's out of range of all these things. It will not be equal to Sunday. It does not automatically wrap around. You can make it, right? Alternatively, you can do something like this, and there are tricks like this. Today is today is equal to today plus, I don't know, 2 mod 7. Right? So if you do little tricks like this, then you can get it to wrap around to the next week. Right? Why? Because there are 7 days. And sometimes people will even put in a dummy value down here, number of values. Why? Because that automatically receives the value 7. So if I use that instead of 7 all over my code and I added another day because now we've got an 8-day week, it would still work. Don't do that though, right? Tricks are for kids, right? We want to write maintainable, readable, understandable code. Some things to note about the style of the program. Right? Well, first of all, that's how you use it. Once you've declared a type, like an integer or a double or a float or something like that, you can go ahead and use that as a type in your program. As far as the styling goes, you use capital underscore casing, just like constants for elements. You use upper camel casing for the name, day of week, to offset it from variables. Types, variables. Generally, white space doesn't matter, but it is good to put them one to a line. I could have mashed these all onto one line, not as readable. Right? Use type definum. You use a comma delimited list inside of curly brackets. You name the type at the end with a semicolon at the end, and generally they are declared in header files. Right? Because you need to include it in your source file, so it needs to be everywhere. It needs to be in the header file. So be careful. In Java, you have an equivalence, right? So Java also has enumerated types. The key difference is that they are not integers. They are their own types. So you can't do little tricks like plus plus. The compiler prevents you from doing that at all. If you want to see more information, like other fancy tricks with enumerated types with Java, just read my book section on it. But otherwise, this is good enough. Right? I can take this entire list over here, this example right here, and just simply move it over to where we did it day of week. There we go. Day of week, and we're done. Please format that better. So in Java, the default the suggested formatting is to mash them all into one line. Go figure. Right? But once you've got that, then over here in the demo class, then you can declare it. So day of week, today is equal to day of week dot Friday. So another part of the syntax here is that you do have to put the class or the enumerated type's name in front of it. Without that, it doesn't work. But as I said, you can't do bad things like this. That's not an integer in Java, so it's going to be a compiler error. Right? But you can check if today is Saturday, day of week dot Saturday, excuse me, dot, then printf, or system dot out, println game day. Oh, there we go. Of course, it's not game day yet. If you are going to do something like this, though, in any real system, bring in a library. Right? The Java time library has days of week, it has durations, it has moments in time, periods of time, et cetera, et cetera. Right? We didn't always have, we always had 7 days of the week? We didn't always have 12 months, though. It used to be more metric. We had 10 months, right? And they all made sense, except that some Roman leaders, what did they call the Roman, like Caesar is? Roman emperors, there we go. They were emperors. They crowned themselves emperors. They needed their own months. So that's where we got July, Julius Caesar, and August, Augustus Caesar. Right? And that gave us the Gregorian calendar. Gregorian calendar, you can still have the Chinese calendar, you can have the Japanese calendar. You've got a million different calendars, except for in the modern world, we all use what's called, the Gregorian calendar now, right? But you could still translate things to other calendars and ways of doing time. Don't give yourself a headache like that, right? Use a library. All right. So what about error handling in Java? Again, it is completely different. Instead of defensive programming, you use exceptions. And what is an exception? An exception is an interruption of the normal control of linear control, right? Statement A, statement B, statement C. Statement B, something went wrong, right? Something happened. So let's just demonstrate that with an example over here in my demonstration code here. Right? Int A is equal to 10. Integer B is equal to 0. Yeah, there we go. I'll go ahead and go with 10 for now. Right, there we go. Now, let's go ahead and try to compute the like double C is equal to A divided by B. Right? Okay. So, and then we'll print it out. System.out.println C. What's the value going to be? Oh, sorry. A divided by 10 divided by 10. 1. Okay. Normal control flow. A, B, C, D. What happens if we try to do something like this? We're about to divide by 0. So what's going to happen? Division by 0, exception. So what happens is we've got this line, an interruption of the normal control flow here happens. That this is going to be division by 0, so it throws an exception back at you, right? We walk up to the edge of a cliff. We don't bother looking, right? If this were C, I would I would do something like this. If B is equal to 0, then I wouldn't do it. Printf error or something, right? I wouldn't end up doing it. But this one, perfectly fine. Just go ahead and jump off the cliff. What happens is you'll be caught and put back up on the cliff, and as long as you've got code to say what to do in that event, then you'll be safe. What we're going to do is we're going to try to do this dangerous operation. And if something were to go wrong, we will catch that exception that gets thrown. What kind of exception is this? It's an arithmetic exception. So let's catch that arithmetic exception. There we go. AE, I'll call it AE. Why? Because there's no other name for it, right? And then we will, I'll still print it up there. We'll print out an error message. Here, this is where we decide what to do with it. So I could say system.error.println cannot divide by 0. There we go. I don't need println. There we go. Right. So we can decide what happens in that case. What happens in that case in a lot of applications is If you're about to divide by 0 or something that is basically 0, that means that the result is very, very large. And so I could set, I don't know, C to be something very large. I mash my keyboard here. Maybe that's good enough. Or I could reprompt them for input. Or I could do something else entirely. I could system.exit on them. Right? What if I don't want to? What if I just want to go on with my life? Right? Oh well, print system.out.println. Oh well, let's do the rest of the program. ... Right, there we go. So now this will happen. We'll print an error message to the standard error, cannot divide by 0, but then normal control flow continues after that. Right? So we will catch the exception, log it, do whatever we want with it, use different values, but then we will move on with our life with the rest of this. Right? Another condition, and this is why I put it as an integer instead of an int, would be null. Now, what's going to happen here? Am I dividing by 0 anymore? Nope. So it's not going to be an arithmetic exception anymore. What it's going to be is, cannot invoke integer to int value because b is null. There's a null pointer exception. Well, what if we wanted to handle that differently? I would catch that null pointer exception instead, NPE. Right? And if you want to be really helpful about it, what you can do is you can go npe.print stack trace. Right? There we go. And let's go ahead and run this again. There's the full stack trace. Right? So this goes all the way back to when we started talking about functions 2 weeks ago. How do functions work? Function calls a function, calls a function, calls a function. What are these things called? Stack frames. Right? So what is a stack trace? Well, it's tracing back all the way back to the beginning of the program. This function called this function, this called function, called function. The error occurred here. Where did it occur? Right? Well, we only have one function here, but you can go to the line number. Right? In fact, it's clickable in Eclipse. Right? I can jump to this line number, read all about it, right? And I can see the control flow of how I got to this place. If I had 5 functions, I would be seeing all of them in this stack trace right here. Right? And it moves on with the rest of your program. Again, if you wanted to, you could go system.exit because I want that to be failure. I want that to be a failure, right? Some things are not recoverable, right? How can you recover from a bad internet connection? You can't. Right? You mean maybe you can try it once more, twice more, thrice more, but at some point you've got to time out and say nope, we can't continue. Right? So it could be a fatal error. In this case, what's going to happen? Am I going to print out? Oh well, let's do the rest of the program. Nope. We just simply end up exiting out of the entire program. Let's restore it to show that if you have normal conditions and no errors at all, none of those catch statements are executed. So what if there's an eventuality that we have not thought about? It could throw an arithmetic exception, it could throw a null pointer exception, it could throw foo exception. Right? You can have a catch-all down here, catch exception E. Right? A null pointer exception is an exception. An arithmetic exception is an exception. All exceptions are exceptions. So if there's some other exception that you haven't thought about, and you can write your own exceptions, by the way, but we won't, then you can catch them all, right? And so system.printf or system.error.println, something really bad happened. There we go. And I'm not going to be able to force it, but of course, under that condition, I'll probably want to exit. Right? Oop, you cannot divide by 0. You cannot divide by null. There we go. That's a better error message. Right? The order matters. The order matters just like an if-else-if statement. The first one of these things to occur is the first one that gets executed. Right? The first one of these things to match. So if it throws a generic exception, that's not an arithmetic exception, that's not a null pointer exception, so it gets caught down here. If I had this up above instead, right, and it was throwing an arithmetic exception, there we go, fix that, and let's go ahead and divide by 0. In fact, it's not even compilable now. Let's read it. right? Unreachable code block. Why? Because if I catch every type of exception right here, this stuff will never ever execute because this is the first one that gets executed. Right? So let me undo, 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 and now it makes sense. Right? So just like an if-else-if statement, the most specific things up here, the most general down here, and you can't get any more general than exception. Right? All exceptions are exceptions. You can also have what's called a finally block. Right? So regardless of an error, or no error, this block is executed at the end. Right? So let me show it to you, system.out.println. Moving on, there we go. There. Now, am I dividing by 10? Okay, so we'll see that this gets executed no matter what. Moving on. Oh well, let's go with the rest of the program. But let me go ahead and divide by 0. Now we're going to get an arithmetic exception, but that moving on will still be printed. Right? You cannot divide by 0 moving on. Why would you want a finally block? You try to do something dangerous, something bad happens, right? But you need to clean up resources or something like that. For example, opening up a file. Lots of things could go wrong. The file doesn't exist. You don't have permission to open up the file, right? Once you open the file, it has bad contents, right? Malformed contents, right? Well, what if the first two things are okay? You opened up the file, you have permission to open it up and look at it, but it's got bad data in it, right? You have a file open. What do you think? This is a preview of file IO we're going to do eventually, but you have a file open. What should you do with it? Probably close it, right? If you don't close it, it could corrupt the file, or you could have undefined behavior. So regardless of whether or not there's bad data in that file, I want to close it at the end. That's a perfect instance of using finally. Right? Clean up your resources at the end. Okay? So that is exceptions. Right? That's a very terse introduction to exceptions, I should say. And again, the philosophy is that go ahead and leap before you look. Right? Go ahead and try a potentially dangerous operation. We'll catch you if you fall, and you'll be able to handle that error. Right? The advantages to this are over the old school error codes are that it actually has semantic meaning. With error codes, they're just integers. 1, 2, 3, 4, 5. Yeah, we made them not magic numbers by giving them actual names, but as far as the code is concerned, they're still integers. Right? But with exceptions do have a semantic meaning. Right? For example, a null pointer exception is not the same thing as an arithmetic exception, which is not the same thing as an input mismatch exception. Right? Those are all three completely different types that the compiler and the language can distinguish between, because just like it can distinguish between an integer and a double. All three of these are distinguishable because we have an actual type that we're defining here. Right? At the end of the day, an enumerated type in C is still just an integer, even though we type defed it. Right? It's just syntactic sugar. Have I said that before? Syntactic sugar, right? Why do we like sugar in our languages? Why do we have 50 different ways to say good? Right? Good, awesome, great, cool, right? Why do we have so many different ways of doing it? Because it makes their language richer. With syntactic sugar, it makes the language not richer, but more flexible and usable. Right? Okay. All right. Unfortunately, another advantage over this is that with defensive programming in C, it often leads to large, huge, nested separate handling code and go-to-fail style errors. I don't know if I've mentioned this before, but let's look at this classic Mac error, go-to-fail error code. Right? So for many, there we go. There it is. For many years, there was a bug in Apple's SSL, which is secure socket layer. So basically any network security at all, that basically nothing was getting checked the entire time. And why? What was the issue? Well, hopefully there's an actual code here. There we go. So that's what I mean when I say that it has a real disadvantage. If this type of error, then I go to fail and I handle it. If it's this type of error, I go to fail and I handle it. If it's this type of error, I go to fail and handle it. Go-to is a go-to statement that will jump down to error handling code, which doesn't look like they have it here. But it would look like go-to with a colon in front of it. It's a named code block. You can do that in both languages. You should not, right? For example, I could say go-to foo. Oh, do I not have go-to? Jump? Nope. Anyway, you can do named. How do you do it in Java? I'll do, say, foo. And then I'll say, I thought this is how you do it. System.out.println, I'm at foo. Yeah, there we go. It just needed something below it. That is a named code block. What's the warning? That's a good idea. Unused, right? So it's never actually used. Never, the label foo is never actually referenced. Okay, can I go to foo? Nope. I mean, it's coming up as a how do I do it? I don't remember how to do it in Java because go-to is considered harmful. Right? There's this paper way back when that this style of programming is very old and it's not real. It's fallen out of disuse for very good reason because you have things like this, right? You've got this big giant if statements all over the place, and you jump to this this fail block. This is the mistake. This line should not be here, right? So because of that, everything at the end was being circumvented, right? I forget exactly how it was. Mistake, this line should be, somebody just copy pasted basically a bunch of stuff. Why would that fail? Go to fail. Say what?
Single line of inheritance.
Well,
Wouldn't that be why?
if this, then it goes to fail. It should just jump down there. You don't really need to know C or to understand the error. It's supposed to calculate the blah, blah, blah.
It doesn't have brackets,
Oh,
it's not in the brackets.
there, well, this would be in the brackets.
But if it's not that, then it's
Thank you. There we go. Right. Also, lack of brackets. Right. What's going to happen here? This is perfectly fine. We do not go to fail. But then what do? This is not bound to this thing up here. So indeed, we jump to the failure mode, and nothing. This thing didn't actually get checked. Right. So there is a go-to fail, and there's a classic paper called "Go-to Considered Harmful." Right. So I mention that because any bad practice it's become you call them memes nowadays, but we just call these idioms no, that's a terrible that's a hackish way of doing that. That's considered harmful, right? And this is considered harmful. Considered harmful is a part of the phrase template. X is considered harmful. Oh, as of 2019, what? It's because of Edgar Dijkstra. Go-to statements considered harmful. What did it say about 2009? Snow clones have. It's snow clones? What is a snow clone? Is a cliche and phrase template that can be used and recognized in multiple variants. In other words, a meme, right? Maybe it's I don't know why they call it snow clone. That's the first time I've ever heard of that. Has been used in titles of at least 65 critical essays in computer science. So they took Edgar's original paper that said you should not be programming like this because it's brittle. It has so many problems with it. You can get yourself into trouble, and in fact, you can get yourself into real trouble here if you screw around. Then you shouldn't be doing it. So it's considered harmful. Right? So go-to fail bugs like that are considered harmful. How do we solve that? Well, through proper modern programming techniques like exceptions. Right? Exceptions, you don't have to have big giant if statements. It still looks like a big giant if statement, but the behavior is completely different. Right? It is now, taken care of by the language instead. Right? All right. The code is the error handling code is located right along with the exception that it belongs to, instead of way down at the bottom, somewhere completely different. All right. Yeah, we've got enough time. Unfortunately, there are some bad types that you have to learn about here. So in Java, all exceptions are subclasses of throwable. There are things called errors, right? Anything that can be thrown. An exception can be thrown here, but an error can be thrown. There is no way for you to recover at that, right? For example, those should always be fatal. The JVM, the Java Virtual Machine, if it runs out of memory, can you download more RAM? No. So what's going to happen is the Java Virtual Machine dies, and it should die because it has no more memory and you can't give it more memory. Exceptions are what you do use in your code. But however, there are two types. There are exceptions, we call these checked exceptions, and then there are runtime exceptions, which are unchecked exceptions. And unfortunately, this is a little quirk of history that you have to deal with in Java. You only have to deal with it in Java because everybody learned their lesson that you do not do this. Right? They put it in the language early on in the language thinking it was a nice and shiny thing to do. Let's go ahead and do it. No other language since has ever adopted this pattern, and for good reason. Right? Let me show you an example. Before I show you an example, let me go ahead and put this into the notes so that you have it. I'm not going to put that into the notes. I do not want you using foo or named code blocks like that. So Java. There we go. So that's in there now. Let's go ahead and try to open up a file. Right? So I'm going to try the way that you do this. I just want to get this code here. Yeah, this. Scanner s is equal to new scanner on a new file foo.txt. Right? There we go. Actually, let me go ahead and take all of this away and show you what I'm talking about with respect to a checked exception. So I'm going to import file, import scanner. Oops, I don't want to create it. I want to import it. Okay, fine. Import java.util.scanner, isn't it? There. It's not compiling. Let's find out why. An unhandled exception type file not found. Right? This is what we mean by a checked exception. You are forced to surround it with a try-catch statement, even if you don't want to handle it. This goes against the design principle that I was talking about earlier. What if we just exited out of the program? We are taking the decision-making process away from you. Java has taken the decision-making process away from us. It has forced us to surround this with a try-catch. In fact, that's what one of the options for this. Just surround it with a try-catch. File not found exception. Right? How do we recover from that? I need to open up this file and I need to process the data. That's all I'm doing. Run it again? Do you think the file will still exist? Okay, it'll magically come into existence, right? No. So if you read the Java documentations, they say, when should you use a checked exception? And it says the documentation said that you should use a checked exception when you can reasonably recover from the error. How do you reasonably recover from a file not there? How do you reasonably recover from no network? How do you reasonably recover from bad passwords? Right? These are things that they designed. Right? They violated their own, they contradicted their own design principle with this. And again, a checked exception is unique to Java. C++ added them, but it's optional because everybody learned their lesson. Checked exceptions are not good. So how do we deal with this? Anybody go fishing? I've never fished before, but any anglers? All right. So do you eat them or do you throw them back? Oh, you eat them. Okay. Sometimes both. Okay. So if they're too small, you what? You catch and release. So what we're going to do is we're going to catch and release by throwing a new runtime exception on E. Right? There. Right? I don't know how to handle that. I'm not even going to bother trying. But I am going to have to surround this with a try-catch because Java forces me to. What I'm going to do is I'm going to, I caught this exception. I don't want it. I'm going to throw it back, right? As a new runtime exception, which is an unchecked exception. And that does not need to be surrounded with a try-catch. Right? So all we're doing is we're catching and releasing. And this is the way that you usually deal with it, right? Usually, you have to deal with checked exceptions by rethrowing them as runtime exceptions. It is just a quirk of the language that they built into it, and because one of the design principles of Java is to be 100% backwards compatible all the last 30 years, right? It's something that we'll have to live with for as long as we have Java. But they learned their lesson. Every library that I know of, modern Java library that I know of, does not use checked exceptions. Everything ends up being a runtime exception. Right? So everybody hopefully learned their lesson on this. No, this is a bad language design here. And now you understand why we have so many languages, right? Oh, that seems like a good idea at the time. Nope. Okay, now we're stuck with it. And then somebody else says, well, we're stuck with too many things. Let's make a new language. Right? And now we've got 101st language. Everybody always comes up with, I can do it better, right? And then, okay, you did it better for you and a couple of other people, and now it splinters off, right? It's the, have I showed the XKCD before? Okay. I guess we can end our Friday on that. XKCD standards. Right. There we go. There are 14 competing standards. Ridiculous. We need to develop one universal standard that covers everything. Yeah. Now there are 15 competing standards. And this is why we have hundreds of different programming languages. Everybody thinks they can do it better. All right. I'll see you on Monday.